Hello everyone. In this lecture, we are going to start a new topic and we are going to focus on characterizing the dynamics of homogeneous turbulence. Um, so what I'm going to do, I'm going to write an equation for instantaneous fluctuating velocity that we already had before, and then do some manipulations and derivations to get to an equation. And then after that, we are going to we are going to assume homogeneity in turbulence, and I'm going to discuss what does that mean to get another equation for homogeneous turbulence. And then we are going to look at spectral equations by taking Fourier transforms, because that's going to give us a lot of important information about the role of different terms in turbulence, like production, transport, and dissipation, so we can better understand how actually turbulence works from large scales to small scales. Okay, so let's get started. So the first thing that I want to do is to define these two instantaneous fluctuating velocities. So UI is defined as UI at two locations in the flow, right? So I want to define these at two locations in the flow. So we have UI xt. So we define it at location x, and this is instantaneous fluctuating velocity at x. Okay. Similarly, we define another notation for velocity, but at another location. We call this uj prime, and we define this as the velocity uj at another location, at location x prime, and time t. Okay, and this is again instantaneous fluctuating velocity at x prime. Okay, so what I'm going to do is I have the equation for, let's say, fluctuating velocity here that we derived, right? I'm going to use that and then multiply one of these to another. A trick that we used before too, right? So we have this equation here. So I'm going to use that in the Navier-Stokes equation, and then multiply one to another. So first we multiply uj prime to the equation, the Navier-Stokes equation, u partial ui partial t plus uk, I write it as uk instead of uj now, partial ui over, so that we don't confuse it with this j here, partial xk, because I don't want to confuse it with here, so I write this as uk, and then equals to the right hand side of the equation, which I'm not going to write again. And similarly, we can do that for the other equation. So I just multiply ui for the Navier-Stokes equation that is written for u prime j, partial t plus u. Now this is going to be u prime. All of these are u prime k partial u prime j over partial x prime k, okay, equals to the right hand side again. So I multiply ui by this equation and multiply uj prime by this equation, and then I sum them up to get a new equation. So I sum them up, and what I'm going to get is this. I'm going to get uj prime partial ui over partial t plus ui partial u prime j over partial t plus u prime j uk partial ui over partial xk plus u prime k partial u prime j over partial x prime k equals to the right hand side. Okay, so now we know that these two, based on the calculus, this is going to be partial ui u prime j over partial t, right? Okay, so this is the first simplification we made. And the other thing we know is that u prime j is not a function of x, right? As you see, u prime j is only a function of x prime and t, okay? So what does that mean? This means that in the derivative here, in this derivative here, right, this acts as a number, so it doesn't matter. We can take it actually inside the derivative, right? Because it's not a function of x, and when it's not a function of x, so it's like a number. Okay, so uk, I can write that uj prime uk partial ui over partial xk, this equals to uk partial u prime j ui over partial xk. Okay, similarly, ui is not a function of x prime. Here you see it. It's only a function of x. So this means that, again, I can take this here inside the derivative because it acts like a number. So ui u prime k partial u prime j over partial x prime k equals to u prime k partial ui uj prime ui over partial x prime k. Okay. Okay. So now when we add this together, we have, I can write this, say the first term here, uk partial, let's say, so I can write this, the first term here, let's say here, this one. Uj prime uk partial ui over partial xk. I can write it like this, right? So I can write it uk partial uj prime ui over partial xk. And then I can add a zero term to that. And what is the zero term? Is uj prime ui partial uk partial xk. And why is this is zero? Because of continuity, right? Because this is the divergence of velocity partial uk over partial xk, so it's zero because of continuity. So I just add this zero term to that because this is going to further simplify my equation. So this is going to be give me again like from calculus, this is going to be partial over partial xk of ui uk uj prime, right? And similarly, you get it for this term too. So this term is going to be this, similar to that. So we get, finally, we are going to get partial ui uj prime over partial t plus partial over partial xk of ui uk uj prime plus partial over partial xk prime of ui uj prime uk prime from here equals to the right hand side, okay? So now I take an average, so take average and assume that there is no mean velocity in the flow. It's the homogeneous turbulence, right? And you have this homogeneous turbulence, you can assume that there is no mean velocity in the fluid, right? So it's just a turbulent flow, okay? So if you assume that, then what we are going to get is as follows. If you take the average here, you're going to get partial over partial t of ui uj prime bar plus partial over partial xk ui uk uj prime bar plus partial over partial xk prime ui uj prime uk prime bar equals to the right hand side, which is going to be minus the pressure term minus 1 over rho of partial p u prime j bar over partial xi plus partial p prime u I over partial x prime j bar plus new viscous terms partial square ui uj prime bar over partial xk squared plus partial square ui uj prime over partial xk prime squared. Okay, so I didn't go through the right hand side, but if you do that, do the same procedure, you're going to get this term here, okay, for the right hand side. Okay, so now I'm going to make some assumptions to further simplify this equation. So, and the assumption I want to make is about the homogeneity of the turbulence, and I assume that we have a homogeneous turbulence. So assume homogeneous turbulence. So if you assume homogeneous turbulence, that's like everything, all the mean variables in all directions are going to be equal, right? It shouldn't matter which direction you are choosing, right? This is the property of homogeneous turbulence. Any direction that you go, if you take an average, then the quantities are going to be similar in a homogeneous turbulence. So for example, u bar, the mean velocity in x1 direction, is going to be equal to velocity that is in the x2 direction, right? So in all directions, the mean variables are the same in homogeneous turbulence. Okay, so this is the definition of homogeneous turbulence, just to further simplify our thing. And then also the other higher order moments like u prime 1, u prime 2 bar at x equals to u prime 1, u prime 2 bar at x prime, right? In all directions, the average of these moments are equal to each other. Okay, so this is going to further simplify our equations. And there is another thing that because of this homogeneity, you can prove that if you take the two moments of any variable, okay, and take the average of that. So for example, u prime I at x, u prime j at x prime, and they take the bar here, take the average. In a homogeneous turbulence, you can prove and show that this, let's say this equals to I can write it as u prime I x u prime j x plus r, and I'm going to show something here where r equals to x prime minus x, okay? So you can show in a homogeneous turbulence that if you take these kind of correlations between 2 points in a flow, okay, in a homogeneous flow, then these are going to be only a function of their distance, which we show that as bij r, okay? So no matter where they are located, the only thing that matters when you are taking these, let's say, correlations, you are calculating these correlations, u prime I, u prime j, for different, say, velocity components. The only thing that matters here is their distance with each other, r, okay? So it doesn't matter if they are located, say, here, or let's say we just rotate this one to here. As long as r is the same, their distance is the same, this is going to be the same in a homogeneous turbulence. Because why? Because it's only a function. In homogeneous turbulence, everything is homogeneous in all directions, right? So it shouldn't really matter. It shouldn't really depend on the direction. And what's really important is the distance, okay? So if they are very close to each other or very far from each other, that's what really matters. So we can prove that in homogeneous turbulence, this is only going to be a function of their distance. So homogeneous turbulence, or homogeneity, let's say homogeneity, implies that the 2-point moments only depend on r equal to x minus x. Okay? So this is important because we are now going to use this property of homogeneity and further simplify our equation, our obtained equation here, okay? So I'm going to do that in the next session, where I'm going to define two new variables based on this distance here, and another variable Kesey, which is the sum of these two borders, and then rearrange the terms and rewrite them by changing the variables from x and x prime to a new set of variables, and then take the new derivatives and further simplify these equations.